Alright, today we are balancing chemical equations, and this is an application of the law of conservation of mass, which we've talked about before back at the beginning of first semester when we were talking about matter, that in a change, whether it's a physical change or a chemical change, like a reaction, that whatever is at the beginning must be present in the same number and type at the end. So nothing can be created or destroyed. All of our reactants and products must be equal in both type, so that would be our elements, and quantity, how many there are. So we're going to balance equations to show that they're following the law of conservation of mass, and also when we do that, placing coefficients in the front. These coefficients are going to also represent the different kind of ratio of ingredients that will be in our reaction. So if you think about a chemical reaction, it's kind of like a recipe, and we need it to equal reactants and products. All of the elements need to be there before and after. They just might be bonded differently. So a couple of terms that we've already seen before, but will be helpful to kind of re-establish here are subscript and coefficient. So a subscript is the small number that's directly to the right of an element in a chemical formula. So all of these, I'm going to underline right here, these little numbers are subscripts, and they apply just to one of the elements, the one that they're right next to. So this is telling us we have 4 oxygens, but it only applies to that oxygen. Same here, the 2 applies to the sodium, again 4 to the oxygen. And so our subscript is communicating the quantity of that specific element. Put that down here. Communicate the quantity of a specific element. Now, if there are parentheses written, then we are going to multiply that subscript through by distribution. So for example, if we have, in the second one, this 2 outside of the parentheses, that applies to everything inside the parentheses. And if I were counting my nitrogens, this would be 2, and hydrogens, it would be 8 because of the parentheses. So that's the only time a subscript will apply to more than just one element if there are parentheses. Subscripts are part of the identity of a substance, so they're never to be changed when we balance an equation. Those tiny numbers are set because they're either part of the polyatomic ion, they're part of the crisscross method that we've used. They are set. They do not change once they have been written. We cannot adjust them when we're balancing. Whoops. Okay, so next we have coefficient. And the coefficient is the large number in front of the chemical formula. And this one communicates the quantity of the entire substance rather than just one element. It applies to the whole compound or molecule that we are dealing with. Okay, so anytime you see a coefficient, it will multiply into the entire compound by distribution. So if I were to have, the only coefficient here we have is this 2, so it applies to everything inside of it. In this one, it's just the sodium. But if I had a 2 written here, it would apply to the copper, the sulfur, and the oxygen. And so my totals would be 2 coppers, 2 sulfurs, and 8 oxygens. So that is how our coefficients work. They are adjusted while balancing chemical equations. That is what we get to use to make sure we're following the law of conservation of mass. A term that we've used quite a bit, just to remind, a chemical formula is the term of element symbols and subscripts. And remember, these Chemical formulas describe the ratio of elements bonded together in a compound. And again, this is why we do not change the compound's subscripts, because they are a specific ratio that is predetermined as its identity. Just like we've said, sulfate is always SO4. And when we do the crisscross method, because of charges, we'll end up having certain subscripts in certain places. We do not ever change the subscripts. LCM, that's just my short way of writing law of conservation of mass, which we have already touched base on, which says that matter cannot be created or destroyed. And so when we are balancing an equation, we are applying the law of conservation of mass. All the atoms must be present, number and type, in the reactants and in the products. The last term we have here is polyatomic ion. And again, we've seen this before, but I'm using it again because when we see polyatomic ions on both sides of the equation, we can count them as a whole unit. Because a polyatomic ion is a group of atoms that act as a unit and carry a charge. Okay. So if we have a polyatomic ion on both sides, meaning the reactants and the products, you can count it together. So this you could count as sulfate and sulfate, and there would be one of each because there's no parentheses indicating multiples. But if it's not on both sides, let's say we only had sulfate on the reactants, but then on the products it was sulfurs and oxygens separated in different compounds, which could happen, then you'll have to split it into sulfurs and oxygens instead of sulfates because it's not on both sides. However, it should still balance because of the law of conservation of mass. You have to have them equal in amount and element type on both sides. So let's go ahead and try our hand at some of these. The first example here is just for us to count the number of the atoms and see if it's balanced or not. So what we will do first when we start balancing is we will draw a quick table here, reactants R, products P, and then we'll list out all of the elements that we see in the reaction. So we've got copper. I'm just going to put them in the order that I see them in the reactant side. I'm going to do the same on the products, even though they're in different orders, so I can see them right next to each other. Then our sulfate is on both sides, so I'm going to count it as SO4 instead of splitting it. And then I also have sodium. Because of the law of conservation of mass, everything should be present on both sides. If it's not, then you did something wrong. Go back and check and make sure you didn't miss anything. You do not need to list your states of matter. Those are just giving you information about the reaction. They're not part of our balancing. So now we count the atoms. We have 1 copper, 1 sulfate, and 2 sodiums. On this side, we have 1 copper, 1 sulfate, and 2 sodiums. And because the numbers match, type and quantity, we are balanced. So this one is already balanced. Yay. Sometimes when we approach a reaction, it will already be balanced. Other times it won't be, like this second example, and we will need to add coefficients to make it balanced. So let's do the same process here and list our elements and polyatomic ions that appear on both sides. So I've got ammonium, and that is on both sides, so I'm going to group it together. Then I have carbonate again on both sides, so I'm going to group it. And then we have chromium and chlorine. All right, let's count. Reactant side, we have 2 ammoniums and 1 carbonate, 1 chromium, and 3 chlorines. On the product side, 1 ammonium, 3 carbonate, 2 chromium, and 1 chlorine. As we're doing this, in the future, as we do more balanced equations, I would suggest counting them before I do it and then unpause and check. I'm getting these numbers from Subscripts. If you thought there were 3 carbonates, remember that the CO3 is part of the group. It would have to have parentheses and then a 3 to be 3 of them. And then again, Subscript is just telling us how many. Again, ammonium, if you thought there were 4, remember parentheses. 1 is implied if there's no parentheses. And if there's no subscript, 1 is implied. Just a little review there, okay, of where I'm getting these numbers. So now let's start balancing. Pick any element or polyatomic ion that is not balanced and start using coefficients, which will multiply the whole compound by a particular number. Now this one is kind of special because you will notice we've got ammonium and chlorine together on the product side, but they're separated on the reactants. If you look at them here, let me grab a highlighter here so we can see it. So we got ammonium and chlorine, and then they're together here. But notice our ammonium, there's 2, and chlorine, there's 3. And so if I were to put a 2 here, one of them would be, the ammonium would be balanced, but not the chlorine. And if I were to put a 3, the chlorine would be balanced, but not the ammonium. So when we have a problem like this, we're actually going to want to use a common multiple between the two numbers, which in this case would be 6. 2 and 3 both go into 6. So we are going to try to get both of them to be 6 by multiplying. So I'm going to update all of my counts because I've added a coefficient. So my 6 now applies to my ammonium. No longer have 1, so I cross that out. And it applies to my chlorine. Again, I no longer have 1, now I have 6. Okay, so now on my reactant side, I'm going to make my ammonium 6, and I have a 2 currently, so to multiply to get 6, I'm going to put a 3 there. And again, we update every time we add a coefficient. That's 6, no longer 2. Carbonate is now 3. And then lastly, chromium and chlorine. If I want this to be 6 on my chlorines, I'm going to put a 2 here and update. 2, no longer 1, 6, no longer 3. And look at that, it automatically balanced out our chromiums and carbonates because it is balanced. Beautiful. Notice we have 6, 6, 3, 3, 2, 2, 6, 6. Now we are balanced. Anytime you have a blank, that's an implied 1. And if you were to have balanced this where you had a common factor, you could pull out of all of these, maybe divide them all by 2 or something like that. Always reduce your reaction.